Okay, everyone, welcome for today. We're going to start the first session with Benedikt Peterseim from University of Bonn, speaking about a convenient topological setting for higher probability.
Thank you very much. I will start with a little agenda and an overview at the same time. And the first point will be the backstory. What is higher order probability theory? Why is it interesting? And this is a story with some twists and turns, and I think you like it. And in particular, I will talk about a certain setting for higher order probability theory of a measurable flavor, let's say, based on so-called quasi-Borel spaces. And the goal of this talk is to translate this story into a topological setting. So this is the reason for the title, a convenient topological setting for higher order probability theory. Next, I will speak about the protagonists in this new story. So there are going to be two new monads, probability monads in the room, the Baire probability monad and the Riesz probability monad. And they are connected to two old friends, the Radon monad and the Giry monad. And when I say Giry monad here, I'm referring to the Giry monad on Polish spaces. I'll say what those are in a minute also. So maybe this is the less famous of the two monads considered by Giry, but she actually considered two different settings, one on measurable spaces and one on Polish spaces, which is already a topologically flavored setting. And this also reflects just how things are in probability theory. On the one hand, you care about abstract measurable spaces and probability on them, but very quickly you also care about convergence. And then you need a notion of convergent sequences. And so topological settings are quite natural here. The third point will be the base category. So I will actually focus on the Baire probability monad, and this is associated to a base category, a Cartesian closed category of topological spaces, which is maybe not so famous, but yeah, this is my favorite Cartesian closed category of topological spaces, and maybe I can convince you that this is something, this is not my invention, but it's still somehow less known, and I find that unfortunate. I think more people should know about QCD spaces.
I want on video.
And then we'll come to the construction of the Baire probability monad. And this is, it's quite nice. There was, I think this was 2 days ago, the talk by Paulo's group in the adjoint school. And they talked about a sort of Riesz representation in order to construct a probability monad. So we're going to do exactly the same thing here. And also one point to emphasize is that maybe at first Cartesian closedness will seem like an obstacle, like something that would make it more hard to construct such a monad. But we are actually going to use Cartesian closeness quite heavily. So it's actually helpful. And then there's going to be the finale, which is going to be quite short. We'll see we have this monad and it satisfies the properties that we want. So that'll be it. So higher order probability theory, what's that? So the basic idea is that you take probability monads and you take Cartesian closed categories and you want both at the same time. So this has important applications in programming languages theory. So this may be nice considering the co-location with MSPS. And yeah, so the fundamental problem with this idea is that the category of measurable spaces is not Cartesian closed. So this is an old observation. And this manifests itself in that there are a lot of subtleties with measurability in the theory of random functions, random functions are also more commonly known in probability theory as stochastic processes. And just a very basic example of this, you usually say a stochastic process is a collection of random variables. You don't say it's jointly measurable in the index set and in the underlying probability space. And these are not equivalent. And maybe sort of the underlying deep reason behind this is this failure of Cartesian closeness. You have all of these bifurcations of concepts, which maybe don't seem to have that much of probabilistic content. But then this is sort of a technical issue, and maybe you don't believe in that. And you say these are issues that can be overcome. Probability theorists deal with this just fine. So here's why you really want to have a Cartesian closed setting for probability theory, because it has applications in programming languages. And specifically, if you want a probabilistic programming language, which is also functional in the sense that you have full support for higher order functions, and you want to interpret this into something like measurable spaces, you run into a problem because this category is not Cartesian closed. And yeah, the basic idea is that you want to be able to interpret programs as probabilistic programs, as probability measures, or maybe more generally as probability kernels, as probabilistic maps. But this is not so straightforward because of this problem. And a remedy for this problem should consist of a base category, C, of sample spaces. So they don't have to be of measurable flavor. They could be kinds of topological spaces or whatever. And this should be Cartesian closed. As I just explained, we want higher order functions. And the notion of probability measure on that category should give rise to a probability monad. Now, probability monad doesn't have a formal definition, really, but we want that the same story that we know from the Giro monad and all of these other settings holds. So we have the unit given by Dirac deltas, we have the multiplication given sort of by a flattening of probabilities. And in the best case, we would like this monad to be commutative so that we actually get a Markov category. And we can apply all of this nice theory of Markov categories to this. And then the fourth condition is somewhat arbitrary, but you could say with the first 3 points, what's the difficulty? You can just take finitely supported measures on the category of sets, and you're done. This is also called the distribution monad, but we somehow also want to be able to model continuous probability theory. Now, one solution was given in this paper, and you can see that my talk is alluding to this, a convenient category for higher order probability theory. And this paper introduced quasi-Borel spaces, which are a Cartesian closed extension of standard Borel spaces. So standard Borel spaces are a specific kind of well-behaved measurable space. And they also gave a notion of probability measure for this setting. And indeed, you get a probability monad, it's commutative. So this works. But there is, so first of all, you may wonder, is it really necessary to invent a new Cartesian closed category for this? This is maybe one question. You may wonder, as for the example of the classical Giro monad, one monad on measurable spaces, one monad on Polish space, is there a topological setting? But then there's also this curious phenomenon, which maybe leads you to thinking that this is not a finished story. And this is the failure of deterministic marginal independence. So deterministic marginal independence actually has a formal definition in terms of Markov categories, but I'll just give you this theorem on how it fails in the setting of quasi-Borel spaces. Namely, there is a probability measure on this product, r times this exponential 2 to the r, so which you can think of as the space of measurable subsets of R, whose marginal on this right-hand side is deterministic. So it's always the empty set. But this joint probability measure is not the product of its marginals. So this is why it's called deterministic marginal independence. Means if you have a deterministic marginal, your random variables are going to be independent. So in other words, independent random variables should be, deterministic random variables should be independent of any other random variable. And I've given you this illustration here of, if you imagine what that means, you pick some number from the uniform distribution on the unit interval, and you get these random numbers and a pair of random variables. And the right-hand side is always the empty set. And still somehow there's a dependence from the right to the left. That seems strange. There's also a way that one can kind of try to explain this. I will not go into that. But I do want to say that this is something that you probably want to at least think about if this is a necessary phenomenon. And I want to say that on the level of monads, as one can show, this corresponds to having a so-called strongly affine monad. So I will also not define this term because it conceptually precisely corresponds to this, at least in this setting. So again, to recapitulate, we have two questions, one following immediately from this previous slide. Is this failure of deterministic marginal independence somehow a fundamental fact of life? That you say, if we have higher order functions and if we have a probability monad and we want both things to somehow work, and we have continuous probability that somehow we will always get these kinds of phenomena. And the second question was the one that I also already mentioned. So can we work with a more common notion of sample space? So quasi-Borel spaces are nice, but they are not very well studied. And maybe you want to think about, can I work with a somewhat more familiar notion? And in particular, is there a topological side to this story? Now to the protagonists. So this is an overview of the probability monads that we have here. And on the top, we have the category of compactly generated weakly Hausdorff spaces. And there are two reasons why we want to work with this space category, maybe. First of all, it's the most commonly used Cartesian closed category of topological spaces in algebraic topology. So maybe one of the practically nice things about that is if you want to know something about CGWA spaces, there are a lot of resources that you can, so they are somehow familiar. They're not something we have to craft specifically for this purpose. And also we have compact spaces embedding into them. So this monad on there, which I call the Riesz monad, restricts down to the radon monad on compact Hausdorff spaces. So that's nice. And maybe I should also emphasize the reason why I called it the Riesz monad. You saw that already in the overview. We will use a kind of Riesz representation theorem to construct it. So hence this name. Then also, sitting inside there, we have weakly Hausdorff QCD spaces. And also, this is not just an inclusion, but this also preserves most of the structure that we care about. So this preserves countable limits and co-limits and exponentials. So I will restrict to this setting, but this won't change what an exponential is or what the co-limit is. We'll take a co-limit somewhere, and it doesn't matter whether you take it there or there. And then from these spaces are Cartesian closed, but they also satisfy lots of countability properties. They are separable, they are sequential spaces, they are Lindelöf, and so they are also they somehow they sit at a sweet spot where the category is nice, but the spaces are also somewhat nice. And inside of QCB spaces, we have Polish spaces, which are completely metrizable separable spaces. And this is one of the very classical examples of probability monads, which you can also recover here. Now we have this overview table. And I guess the most important column here is this enriched over Cartesian closed category. So this is what we are aiming for with higher order probability theory. And you see here we have quasi-Borel spaces, and we have these two new monads. And then you can also see their topological settings. We have the Giro monad, the Radon monad. So this Giro monad, we also have the other one. And then these two new ones. And then there's also the question of whether we have a strongly affine monad. So does deterministic marginal independence hold? And here with the classical examples, we can say yes. With QBS, we have failure, as we saw before. In the case of CGWH spaces and the Riesz monad, I don't know. And finally, for the Baer monad, we actually do have a strongly affine monad. So now the base category. What's a QCB space? QCB stands for quotient of countably based space. So this is a space for which there exists a second countable space Y and a topological quotient map from Y onto X. And in addition, X is weakly Hausdorff if limits of convergent sequences are unique. So in general, weakly Hausdorff means something different, but in case of QCB spaces, it's equivalent to this just uniqueness of convergence of limits of convergent sequences. Yeah, we use that notation, this notation that we already saw in the overview, QCBH for the category of weakly Hausdorff QCB spaces. Now, examples. Every separable metric space is second countable and hence a weakly Hausdorff QCB space. So no surprise here, I guess. But there's another example that I think it's quite nice that we have this example. It's the space of tempered distributions with the strong topology. And this is not a metrizable space, but it does turn out to be a QCB space. And you may wonder why I put 3 pictures of a QR code and an old times television there. So this is supposed to be white noise, sort of the stereotypical random element in the space of tempered distributions. And if you go from the left to right, you have some kind of convergence. And it's quite nice that we can also model these kinds of, you also call them generalized random fields with this setting. Now, the important fact is that weakly Hausdorff QCB spaces are Cartesian closed with countable limits and colimits. And all of this structure is inherited from the inclusion into compactly generated weakly Hausdorff spaces. An important remark, QCB spaces are sequential spaces. So in contrast to general topological spaces, their topology is determined by convergent sequences. So a sequential space is a space in which a subset U is open if and only if for any sequence converging to some element in U, the sequence is eventually in U. So we can recover the topology from the convergent sequences by saying the open sets the open sets are exactly the sequentially open sets. So what I'll do in the sequel to describe QCB topologies is describe convergent sequences in these spaces. And I think in contrast to the more general setting of compactly generated weakly Hausdorff spaces, this gives you, in all of these cases, a very concrete feeling what these are. For example, the exponentials. So the space of continuous functions between weakly Hausdorff QCB spaces x and y can be described as follows. A sequence of functions converges in the space of continuous functions from x to y, if and only if it converges uniformly on compact subsets, if and only if it converges continuously, which is this variation of pointwise convergence, where you require it to converge not at every point, but sort of at every simultaneously, jointly, at every convergent sequence. So the next example is going to be important for the construction of the bare probability monad on weakly Hausdorff QCB spaces, because it's going to be the protagonist in our Riesz representation theorem. So the dual of this space of continuous bounded functions is going to turn out to be the space of bare measures on X. And you might say, I know what the topology on CB of X is. It's a metric space, it's a normed space. But this may, in general, so unless X is compact and separable, this may not be a QCB space. And even if you move to the more general setting of CGWH spaces, the norm topology on CB loses a lot of information. So this functor CB, if you take it to carry the norm topology, will factor through the Stone-Check compactification. So you lose all of this information. And that's why we want to consider a different topology. And this is not a bad thing, because there's a very natural topology on this space. It's sort of the most natural topology you can put on this space, because what is a bounded function? A bounded function that is a function that's bounded by some constant. So it's in this union of functions that are bounded by a specific value. So it should be a co-limit. And that's exactly what we do to define this topology. And this is also well defined because this co-limit to sets is preserved. So this is indeed the right union. And again, we have a very concrete description of convergence in this space. A sequence converges in this space CB of X if and only if it's uniformly bounded by some constant, and it converges in this exponential. Now we come to the construction. So as I said before, this is based on the idea of a Riesz representation theorem of interpreting measures as functionals. So in other words, what we need to know is that we can represent a functional as a measure, because it's the measures that we're after. We want probability measures, but working with functionals is somewhat more easy, because what you end up with is a double dualization monad, or as it's also called, a continuation monad. And this is also quite nice, because this is one way to make precise maybe that something that's already folklore among Haskell programmers, that you can use the continuation monad into floats to do probabilistic programming of some sort. So here's the theorem. The continuous dual of CB of X with the topology that we just defined. So the set of all continuous linear functionals on this vector space can be identified with the space M0 of X of finite complex bare measures on X. So in the end, we'll be after probability measures. But at the moment, we want to consider signed or complex measures in order to be able to use this kind of functional and analytic doubly dualization. And this duality is given via the usual bijection, where you associate to a measure the functional that integrates against this measure. And now this means that the space of complex Baire measures on X also acquires a weakly Hausdorff QCB topology just by taking the topology transported from this CB of X dual. So the CB of X dual is a subspace of the space of continuous functions on CB of X. So we have an exponential on this, and we just take the subspace topology. This is a closed subspace, and this turns out also to be a weakly Hausdorff QCB space. And in this way, M0 of X also carries a weakly Hausdorff QCB topology. Now again, we can describe convergence in this space. And this now just follows from the characterization that we had for the exponential. Namely, we have a variation of weak convergence. You might call this continuous convergence of measures. So a sequence of measures mu n converges to mu if and only if, for all sequences of functions fn converging to f, we have that these integrals of fn against mu n converge to the integral of f against mu. And now you may think that this is somehow bad news. There is an established notion of convergence for probability measures, which is weak convergence, and we get the wrong notion of convergence. But this is not actually the case. In the cases that are where weak convergence works well, we can actually recover weak convergence with this. And if you like probability theory, you can try to prove this, that this convergence follows from weak convergence for Polish spaces. As a hint, you'll need a theorem called Prokhorov's theorem, probably. So this maybe also shows that there's some non-trivial probability theory actually going on. Now we don't actually want to work with M0, but we want to work with this M, which is constructed by taking the closed span of the Dirac measures on X. So we first take finitely supported measures, and then we take the closure of that in the space that we've had before. And now this is one point where we use Cartesian closeness in a very essential way. We can show that all of these maps are well-defined and continuous. And sort of the reason why we can do this easily is that we have this rich representation. So maps like these actually become complicated higher order functionals, and also with this push forward map. And for higher order functions, for these types of compositions of evaluation maps, we know that they are continuous because of Cartesian closeness. And I should say that the continuity of the first map deserves special attention, because we have that with this structure, we get an enriched monad on this Cartesian closed category. And enrichment corresponds to the continuity of the first map. And maybe I should say what this means on the level of probability theory. So this is also something that I haven't seen anywhere before that may be interesting. If you have, so the idea here is that if you have a sequence xn converging to a random variable x in distribution, and you have a sequence of functions converging uniformly on compact subsets, then you can conclude that we have this simultaneous joint convergence. So that's what topological enrichment means here. We have this joint convergence, this joint continuous mapping theorem. So if you just had one F here, then this would be called the continuous mapping theorem in probability theory, that you cannot only just substitute deterministic sequences into your continuous function, but you can also substitute sequences of random variables. And here we have a strengthened continuous mapping theorem. This is topological enrichment. So now one very important question is M commutative? And the answer is yes. And this, as always, corresponds to a Fubini theorem for this kind of measure. And we have a sort of unorthodox proof of this because we don't work normally. You work with approximating on the side of functions. You first look at rectangles or some like Cartesian products of measurable sets, and then you approximate jointly measurable functions with these sets. But here we can approximate with finitely supported measures. And because of Cartesian closeness, let's say because of this thing that everything is continuous, we have joint continuity in these variables mu and nu. And so we can lift this conclusion from finitely supported measures to all measures in M of x and M of y. Yeah, so now we come to the finale, the bare probability monad. So far, with this Riesz representation theorem and this monad M of x, or M that we constructed, we were speaking about signed or complex measures, and now we want to pass to probability measures. And what we do is we just take the subspace of those measures which are probability measures, and it turns out that the structure restricts, and the reason is quite simple, because this flattening operation will give a probability measure when carried out over probability measures. Dirac deltas are probability measures, and push forwards of probability measures are also probability measures. So this is not so surprising, perhaps. And what we also get as a bonus is that our monad is strongly affine. Now, I guess I was a bit more quick than I expected. I already come to the takeaways. The first one is that in addition to the measurable flavored setting of quasi-Borel spaces, we also have a topological setting for higher order probability theory. And we saw that the construction is perhaps interesting because we actually make use of Cartesian closeness. It's not an obstacle. And we have this categorically natural version of the Riesz representation theorem, where we put on CB this topology, which seems like there could be no other topology on CB because it's given by this co-limit over exponentials. And the next takeaway is higher order probability theory and deterministic marginal independence are compatible. And this points maybe in an interesting direction, because you can ask, how much can I tune Markov categories sort of for nice properties? And I think this is something that hasn't been explored that much. There are, especially if you try to simultaneously optimize both the base category and the probabilistic properties. So the very classical topic is sort of nice properties of categories corresponding to nice properties of type theories, where you have the hierarchy where you start maybe with Cartesian closed categories, then you have locally Cartesian closed categories, and you have toposes. And on the other side, we have now this nice language of Markov categories where we can formulate general axioms what probability theory might satisfy, or what we might wish from a setting of probability theory. So now maybe the question becomes, how much can we simultaneously optimize both directions? Are there some fundamental constraints in some direction? And finally, we also observe that it's not necessary to completely come up with a new Cartesian category, but we can work with familiar objects like topological spaces to get a setting for higher order probability theory. So this is on the side of topological settings, where we do care about continuity of our maps. So maybe another question that arises here on the measurable side, are there somehow ways to work with more familiar objects? And maybe one direction that I've heard about is that I would find interesting personally is, I think it was Alex Simpson in some talk who said that he's going to make a controversial statement. A convenient category for higher order probability theory should be the category of sets. Yeah, and this concludes my talk. I thank you for your attention. Here are some references. The first one is my master thesis, which is more of a broader exploration of interactions between functional analysis and category theory, applied category theory. And then there's this paper, which is a bit closer to this talk, but maybe also still a bit unstable. More of a work in progress than I would like. But yes, thank you for your attention.
All right. Any questions in the audience? Maybe we start with that.
Thanks for the talk. You said there are no optimization of probability.
There's no what?
Optimization, like
Yeah, no, I don't think so. I guess the minimal requirement would be commutativity, because then you get a Markov category. But then there are lots of Markov categories which are about sort of generalized non-determinism, like power set monad or something like that, which is not really about. So I guess maybe also having an affine monad is probably also something that you want of a probability monad, so that you exclude signed things and things where you have interference or something like that. But I don't think there's a general definition of what a probability monad is.
Yeah. So in one of your first slides, you had a few requirements, and the last one talked about the unit intervals, the one and I did not come back in your talk, but so I would maybe have expected something like an infinity theory as a requirement, so that
Sure, that would be a better requirement, yeah. But I don't have a Definetti theorem for this. So yeah, I'm not sure whether it would work, but so I don't know whether you could make this also simultaneously work. Yeah.
Yeah, but to be explicit for your new monad, Definetti does not hold, or you have not.
I don't know. I don't know.
So I'm gathering that it's
that's quite unlikely. I always feel uncomfortable making confident statements about things that I haven't actually proved. But I would say 99.9% it isn't, because that would mean your disintegration would have to be continuous, and that's, I mean, you could come to speak to me and we work out an example where the disintegration is discontinuous, and it shouldn't be hard. But again, I haven't done this.
Sorry, could I, yeah, Andrew?
If I guess it's not additional, then do you think there's a modality or
That would be a question for future work, I guess. Yeah.
I guess I'm looking for find my market category. Could this affect this by any chance? Because it's from the find that.
Yeah, so I've only heard of the connection between this and effectuses, and I don't really know what they are, so I'm afraid I can't answer this question. Okay, so maybe that would also be a thing to look at. Yeah.
Hello?
Yes, thanks for your work. It's beautiful. I have a million questions. Maybe I'll save some for the break, but maybe
Yeah.
a couple one. First of all, there are probability monads on the whole of topological spaces.
Mhm.
For example, the one that takes valuations or evaluations, and the ones that like extend to measures. Do you know if this monad restricts to like is there a restriction of this monad to those spaces?
So do you mean, is there so does the monad on all topological spaces restrict down to these ones? So I think the answer is no, because the topology that you use in the case of all topological spaces is the A topology. And yeah, while I haven't checked in detail that this doesn't give a compactly generated weak Hausdorff topology, I would say it's very unlikely that it does. You would maybe have to take some Kification or something like that, and then see if it's still a monad, which is also not very likely, I guess. So I guess, unfortunately, the answer there is no. But there are some subclasses where this does hold, like Polish spaces and compact spaces.
And another question that maybe goes a little bit the direction of the definitive. Do you know if we have a version of the model class theorem or the pi lambda theorem for this monad? As in, is it true, for example, that a measure on a product can be tested by just looking at products of functions on a two-factor?
Yeah, this is a good question. So yes, for the QCB space, because of the Lindelöf property, this should be the case. Yeah, for the latter category, it's very probably not the case, I would say. But so this is why you want to work with. This is sort of the motivation behind passing to limits of finitely supported measures, so you can instead work on the side of measures instead of functions.
If the theorem like that exists, then it's very likely that the Markov category is observationally representable, which means pretty much that the uniqueness part of the finite holds. You can distinguish two measures by taking repeatedly independent samples. The fact that the existing part, of course, is still there. But this way,
that would be very interesting. But would you also need this kind of theorem then on the side of infinite products, or something like countably infinite products?
Well, like a Kolmogorov extension problem.
Yeah, I mean.
Well, actually, there was something I wanted to ask you about that, but even if you don't, you can test with like repeatedly independent copies of finite length, just arbitrarily large.
Okay. Yeah.
There is the limit that corresponds to like testing on an infinite sequence. You don't have the limit, and you can just take the code. Do you have to?
Yeah.
So I have the feeling that the chair was.
All good for now. Let's continue.
It's a historical question. Actually, QBS, but not the probabilistic coherence cases. If this often happens, but I don't know why.
I guess you caught me on something there because I don't really know what probabilistic coherence spaces are. So I have to defend myself, I have to say that I somehow moved towards this application from a different direction. So I was doing this functional analysis and applied category theory here. And then I noticed there might be a nice application to probability monads. And so my background is not actually, so I didn't actually come from that direction in my defense, but I'd be interested in learning about that, definitely.
There are different style of model, I would say. The linear logic model as opposed to a probability model.
Okay.
So, okay. Any more questions in the audience? No, then let's thank the speaker again. And we have a bit of time left, so we continue in 15 minutes.
Congratulations.
That's wonderful. Very nice talk.
I have another
Yeah, sure.
question.
Yeah, so I've looked at the algebras of the variation of that monad. Specifically in the quizzes, I looked at the correctly supported measures. And there it turned out that, so you can get so far that you can say it's a full subcategory of vector space objects internal to CGWH spaces. But I couldn't really characterize in a more like vector spacey way what kinds of vector spaces they are. But I found an approximation from below, which is like the requirement that we map into a double dual inside of this. So inside of the internal home coming from that category, that this is a closed embedding, that's sufficient for this being in the vector space being in algebra for the monad. So, and then for this monad, I was actually talking about to Ruben about this. I would conjecture that some of the algebras should correspond to some kind of so-called stack space, which in addition to the topological vector space also has a norm. But the topology doesn't have to be the norm topology, so that you sort of get an additional unit ball.
So you can say that things are somewhat bounded, so interconnected.
Yeah, exactly. That's it.
So in that I was wondering, like, what's the difference between systems? The algebra that you have. I thought like maybe like algebraic properties.
I'm not sure what you mean.
Well, like basically you're not changing the algebraic, like you change the like you're just giving it a new topology.
Oh, you mean the CB if there's some kind of like Gaussian duality or something? Yeah, this is somehow difficult. So there is a Stone-Weierstrass theorem for Lindelöf spaces, but it has some additional requirements, like you don't want just point separation, but separation of points in closed sets. So you probably need some additional regularity condition on your space. And then there are also so-called quasi-normal QCD spaces, which do have this kind of regularity condition. So yeah, this would also be a future direction, I guess.
You know, it sounds like real valued function space, maybe with some norm again.
You want a matrix?
So form an algebra for what?
This
Yeah.
and take like continuous functions from say R to R.
Yeah,
okay.
okay.
Do these form a mononomial pointwise?
But it's so.
Pointwise. Do these form an algebra?
But in general, it's never used.
So they would form an algebra for the compactly supported monad, but I don't think for the general monad, because you could you could take some unbounded, so
Yeah.
large growing function on this function space and try to integrate it, and it wouldn't work.
No, I think like you mentioned that you
That's always.
have some kind of
I did have
norm.
one other thought, I think.
Yeah, but then you need a norm on all continuous functions from R to R, and that are usefully possible.
Right, as well as. I wanted to talk about
That R is not.
It had to do with your
Or just the other positive real line.
language,
An algebra for the
sort of.
Yeah, essentially, yes.
Opposed.
Yeah.
Because it equals like it's the same.
I mean, I guess one could take an that plus a point.
No, I was very inspired by the basic idea behind that.
That
Sort of, I think, you know, could we use
No,
that?
I guess the problem there would be to join a point at infinity.
Our model.
So at least when you do it in a point compactification way, you need your space to be locally compact.
You know.
And some topological vector spaces are only locally compact when they're finite. So that's somehow doesn't work.
Have almost.
So no, there's just a theorem that an infinite dimensional, so that a topological vector space that is locally compact is finite dimensional.
Oh, you mean?
But then, when we were discussing this,
So I was talking about one point compactifications. So when you take the one point compactification of a space that's not locally compact, you get a non-Hausdorff space, somehow things collapse.
that came up.
Yeah.
And I think someone said that we should. talk with
Okay.
Dave
Yeah, maybe you were.
Because, there was some recollection that.
No,
There may have been,
what I mean is that for the
like, that may have helped.
the G removal,
Some.
yes.
And there were two hypotheses.
there's
One of them was that it was,
there's an algebra structure here that is P to like
performance was, another one was like
if this number is
Somehow-
finite,
the results of
infinity up.
of this interaction with this topological temporal.
Yeah, I guess that potential problem is continued.
Statement or like.
Yeah, that's what I'm
You
saying.
weren't able to.
Here a
understand
splice in the space.
Yeah,
For measurable spaces is fine, right?
results.
Yeah.
But like, and you can take like something like a neighborhood of this one.
Anyway,
So
there's thought.
I wouldn't expect this to work in
Good things to talk
the
about.
continuous case, but since you managed to make work a lot of stuff that I didn't expect to work, and suddenly you're setting it works, maybe this one works too. So.
I think the topos is a nice topo.
So what was it that you didn't expect to work?
For example, that you get deterministic marginal dependence.
Okay, what's
Yeah.
the reason why that shouldn't work?
I was expecting to get the same thing as in quasi-worlds, is that you have this kind of privacy.
And that was
It
mine.
makes sense that continuity kind of avoids that.
Yeah.
But like, to actually find an example where this happens surprised me a
That's
lot.
the question.
it's
that I
interesting-
wanted to
it's
ask,
interesting
and then
that you-
thinking about it, I realized the question doesn't make sense. Like it really.
Like why?
It's really
What's different in the topological
No, I understand that.
of the Borel sets?
Well, basically, in the measurable space, you can like test single points like that.
Yeah.
But that's not gonna be.
Over what time?
Yeah.
And but like, I still
So is
this notion that we continuously avoid this problem is still like really nice. Like, it makes sense, but I don't want to think that into. And instead it's.
in quasi-Borel spaces, I would always ask, what is this function space? Because that's the kind of, we get function spaces with a lot of work, and then we classify things like this. And this is very interesting because there's the space of Borel sets. And I'm asking, what are measurable properties of Borel sets? And
Yeah.
you get stuff like, I don't know, bare category or measure.
Yeah.
But for example, cardinality is not measurable. And that's the essence of this failure of deterministic marginal independence. But the quest, like if I try to ask this in your category, it's really different because there aren't even continuous maps like this.
Yeah.
So maybe we have things like
I could explain why you don't want it. And then, but